Hi everyone. So today we're going to go through the two derivations that relate to double slits and how we get the formulas. Alright, so the hardest problem when we are trying to derive this formula is actually trying to understand what's happening inside the apparatus, or what's actually happening in the experiment. So this diagram here is explaining the setup of the experiment, and so before we even start to derive, it's really important to understand some of these approximations that are needed to derive the formula. So over this side we've got our slits. So here's our slit 1 and slit 2, and they're separated by a distance of little d. So I'll put that over here, a little d. So from the center of one slit to the center of the other is a small d. The other thing that we have here is we've got our length of how far away the viewing screen is. So that's talking about this length here. Yeah, so how far away the screen is, and that is our capital L. Now the center line here, and I'm just going to try and use a different color. So this line here, that from point O over to point A, that's sort of our midline. So that's our reference point. The other thing we can see over here is on our screen, which is down this end here. So this here is our screen down here. We are going to be at a reference point called P. So you can imagine it along this point down over here, we've got bright fringe, dark fringe, bright fringe, dark fringe, and we're all the way up to at point P, and this we're looking at a maximum. All right, so we're at a maximum at point P. Some of the other things that we have here is that the line of light, or the wave coming from slit 1 from here all the way to point P, that's slit 1's sort of light, and the one here coming from slit 2 is meeting up at point P as well. All right. Now, some assumptions that have to be made here. The first one is that L is much larger than distance D. So our screen is much further away than our two slits are apart. So that's really important to note. The next part here, we're talking about S1P. All right, so that's S1 is over here. S1 up to point P is nearly parallel to S2 up to point P. And the reason that's nearly parallel is because they're so close together. Our D value is so small that if we are at a point that's really far away, which, in comparison our L distance is very far away, then those two lines are almost going to be parallel. Okay. We're also working under the assumption here that theta, and remember that theta is the angle of the viewing, like the viewing angle. So if we're standing at point P, let me just choose a different color. Let's go yellow. So this angle here is angle theta for our viewing angle from point P down to that midpoint between the two slits, O. Okay. Now the other thing we have to be aware of is that S1P, which is our top line here, S1 up to P, and RP, so let me just draw it. S1P is this line here, and R to P, R up to P, they're going to be the same length. All right, and what that tells us is that the bit that's left over, and I'll try and use another color again, let's go back to blue, this distance here, which is going to be from S2 to R, that's going to be the path difference, or how much longer that this S2 wave is going to be. So that's our path difference, and remember it's this little guy here is a lowercase delta, and that represents path distance. Okay, so hopefully that's explained the setup, and now once we have all that understood, we can actually look at deriving the formula. Alright, so here we've got kind of a truncated version of that diagram that we had before. So if we recall, this dotted line here, if we kept going up here, that was going to take us to that point P. Okay, A, that was our midline, the midline that was going all the way across to the center of the screen. And instead of down here, we don't have distance anymore. That's represented by our path distance, or lowercase delta. Okay, so now if you haven't seen an angle symbol before, that's what this guy here is, the angle that's between S1, O and A. So if we follow this, there's S1, so this is talking about that one, O, which is over here, and A, which is over here. So you can see that is 90 degrees. So that tells us that the angle between S1, O and point P, which is S1, O and point P, is going to be 90 degrees minus whatever our theta value is. Now, as theta is very, very small, and just for ease, I'm going to rub that line out so that we can see what we're talking about. As theta is really, really small, the lines S1 to P and S2 to P are nearly parallel, okay? We talked about that before. Because L was so big, sorry, it's not writing very well, and because the D, or the distance between the slits, was small. Sorry, my pen's not working particularly well. It was small. So to an O to P, so O is a point here, O out to P is all. So all those three lines, this one, and this one, are all said to be parallel. So that tells us that S1R, and let's follow that around, S1 over to R, which is talking about this line here, S1 down to R, is nearly perpendicular to that dotted line in the center there, OP. And that tells us that to a good approximation, the angle between S1 and S2 and R1, so this angle here, let me circle it in yellow, so this angle here is exactly the same as this angle here. So you can almost superimpose this big triangle on its side and get this triangle here. So those two theta values are the same. All right, so let's have a look at our small triangle, and I'll just rub out my scribble again here so we can see what we're looking at. And we're going to use our small triangle, which is this one here. All right. And we're going to try and find, well, we know, our sine theta. So what we're trying to find here is our angle, I guess. So if we are looking at our sine theta, and we've got, this is our right angle down here. Okay, we have opposite over adjacent. Okay, so we've got this. So the value S1 to R, yeah, and sorry, S2 is our opposite, and hang on, there we go. Sorry, I'm getting confused myself now. So we've got sine theta is equal to opposite over hypotenuse. So our opposite is going to be from S2 down here over to R, and our hypotenuse is going to be this number here, so this distance here, which is going to be our D value. And we know that from S2 to R equals our path difference between our two slit distances. So once we have that, we've now got sine of theta is equal to the path difference divided by D, okay? And we know we're talking about maximum, so our path difference is going to be 1, okay? Or 1 wavelength, okay, because we're at a maximum. So we can rearrange that formula to now have D move to the other side. So D sine theta is equal to a wavelength. So that there is our Young's double slit formula. So we can use this formula to find D, the distance between the slits, or the viewing angle at a particular point on the screen, or if we have all that information, we can actually find the wavelength using this equation. So it's really handy. All right, so in Young's double slit experiment, for reinforcement to occur or for a bright fringe to appear, we need to have a whole number of wavelengths being our path difference to be a whole number of wavelengths, so that we've got a crest meeting a crest, So we've got reinforcement. So that means that our formula that we have to use, let me change color, is going to be the path difference is equal to m being a whole number multiplied by the wavelength. So that makes the formula that we've just derived, this one here. So d sine theta is equal to m wavelengths. So just as we've worked out before. If we're asked in a question to try and find anything to do with the dark fringes on the screen, or the patches of annulment, or the destructive bands, then we need to try and figure out what it is in our formula. So if we have destructive interference, or we have annulment happen, it means that the wavelengths are going to be out of phase, or sorry, the waves are going to be out of phase by exactly half a wavelength. So that way we have peak meeting trough, which means that we have the wave being annulled. So that means that the path difference is going to be m plus a half wavelength. So we can put that into our formula that we've just derived, and now we end up with this one here, which is d sine theta is equal to m plus, that's meant to be a half wavelength in there, and where m is your whole number of fringe points. Okay, so the next thing that we have to be able to derive is a formula for the fringe separation, or how the bandwidth of our interference pattern, and it's also denoted with a delta y. So here's another interpretation of a young double slit experiment, where we've got our light source going through a single slit, then passing through a double slit, and our screen over here. Now the difference here is what we're not looking for trying to find the viewing angle like we were in the previous derivation. We're actually looking at the patches on the screen. So here we're looking at two consecutive bright bands, which means they have to be next to each other. They don't have to be the first two closest to the middle. They can be any distance out, but they do need to be next to each other. And we can see here that this is the middle of one bright fringe going to the middle of the next bright fringe, and that's called the fringe separation, or delta y. Now, point to note down over here is that we've got the distance from the center is going to be, we're talking about bright fringes, so it's going to be y of some value of m, and the next one, because it's the next one along, is going to be y some value of m plus an additional 1, bright to bright. So let's see how we can put that into a formula and actually work out what the fringe separation, or delta y, is. Alright, so the first thing that we have to do is work out, we're looking for the distance, the difference between the two y values, or trying to find delta y. So that means we have to take the one that's furthest away minus the one that's closest, and that'll give us an approximate, like a value for delta y. But if we don't know these values, then we have to try and figure it out. So what we do have, if we draw our scenario, sorry about the crudeness of my drawing, is we've got this is going to be the distance of the screen away, and over here we're going to have a value of y. Now we might have y of m plus 1, or we could have y of just m. So they're the two options depending on which point we're looking at first. So you can see here that we've got two sides of a triangle, and we can use those to know that it's tan, because we don't have a hypotenuse. So straight away we know that we've either got tan of theta of m plus 1 is going to be y of m plus 1 over L. Or the alternate scenario that we may have, if we're just looking at this one here, is we've got tan of m and y of m over L. So if now we're trying to work out delta y, we can rearrange that to get rid of the denominator and make it length times tan theta of m plus 1, take away length times tan theta of just m. Now one of the things that we need to apply here is looking at the scenario, we have to use common sense. Now if our value of L and the distance of the screen is very far away, and those lines were nearly parallel, then our value of theta is going to be really small. So what we can assume is that tan of theta in this instance is going to equal sine of theta, because it's such a very small value. So what that means is that we can substitute sine into that formula that we've just got from our little triangle drawing up there. So if we pop our value, we put our denominator back just so we can see the comparisons. We've got one scenario using the big value of y, which is this one, and one using the smaller value of y. So this is our current scenario. So from here we can put it into 1. Alright, so because we're considering the bright bands or reinforcement, we know from our previous formula of the distance between the two slits multiplied by sine theta is equal to m, or a whole, like an integer, multiplied by the wavelength. So we know that L is the distance from the double slits to the screen, and we've worked out that delta y is the distance between the two adjacent maxima. We also know, because angle theta is very small, and to a very good approximation, sine theta is equal to tan theta. So what that means, if we've got our previous formula, we can try and put that into 1. So instead of sine theta, we've got tan theta is equal to delta y, or the fringe separation. So where's our little triangle again, so we can compare. Sorry about the poor triangle. So this is L, and this is our delta y, which we're still not sure about yet, but we know that it's there. We can say that sine theta, or tan theta, which is equal to sine theta, is equal to opposite over adjacent. So we have this formula here. All right. Now, our original formula of d sine theta equals m wavelength becomes, okay, because we can substitute our, still have our d, so we still have our d. Instead of sine of theta, we put this in here, yeah, is equal to m over, m multiplied by wavelength. Now this, because they're going to be adjacent, that's going to equal 1. So we don't need to have an m value in there. So we can't we've done all of that, we can rearrange and get this new formula here for the fringe separation. Okay, so the reason this works is because sine for very, very small angles is equal to tan theta, which we had originally, so we can substitute in our sine theta formula that we've already derived. So instead of sine theta, we can pop in delta y over L. So we get this formula here, and then we can rearrange it because they're adjacent maxima. There's no value of m because m equals 1, and we have a new formula for fringe separation.